From Einstein's theory of relativity to the mind-bending mysteries of quantum mechanics. From the explosive origins of the Big Bang to the eerie invisibility of dark matter, these ideas are not just theories. They're gateways to a universe beyond imagination. But what if there's more? What if our universe is just one of many? Or brace yourself, what if we're all living in a simulation? Embark with us on a journey to uncover the universe's greatest mysteries, diving into mind-bending theories that will expand your imagination. Together, we'll travel through the cosmos, unlocking the secrets of existence. Theory of relativity. Developed by Albert Einstein in the early 20th century, this theory reshaped our understanding of space, time, and gravity. It's divided into two parts: general relativity and special relativity, each revealing unique insights about the universe that continue to shape science today. Let's dive into general relativity, introduced by Einstein in 1915. Unlike earlier concepts of gravity as a force acting across space, general relativity describes gravity as a result of curvature in the fabric of space-time. Picture a stretched-out trampoline with a heavy ball in the center. The weight of the ball creates a dip, causing smaller objects to move toward it. In the same way, massive objects like stars and planets create similar dips in space-time, which draws other objects toward them. This is how general relativity redefines gravity as the bending of space and time itself. This idea of space-time as a four-dimensional entity where mass and energy can cause a curvature was groundbreaking. The closer an object is to a massive body, such as a planet or a star, the stronger the gravitational effect it feels due to this curvature. In 1919, general relativity received its first experimental confirmation during a solar eclipse. Astronomers observed that starlight passing close to the sun was bent, just as Einstein had predicted. This phenomenon, known as gravitational lensing, occurs because massive objects, like the sun, bend the space around them, causing light to follow a curved path. Today, gravitational lensing remains a valuable tool in astronomy, allowing scientists to study distant galaxies and even detect objects that would otherwise be invisible. The implications of space-time curvature are profound. For example, in areas where mass is exceptionally dense, such as in black holes, space-time curvature becomes so intense that it collapses into what's known as a singularity, where gravitational forces become infinitely strong. At a singularity, the known laws of physics break down, creating an area where even time may cease to exist as we understand it. Einstein's equations in general relativity also hinted that the universe could not be static, eventually leading scientists to discover the expansion of the universe and support for the Big Bang theory. This concept is foundational in cosmology and helps us understand the vast structure of the universe. Moving to special relativity, which Einstein introduced in 1905, we encounter another revolutionary idea: the speed of light is constant, regardless of the motion of the observer or the light source. Special relativity specifically applies to objects moving at constant, non-accelerating speeds and fundamentally changes how we understand time and space. According to this theory, as an object nears the speed of light, time slows down for it relative to an outside observer. This phenomenon, called time dilation, has been observed in experiments where fast-moving particles and clocks flown around Earth experience measurable time differences. For example, GPS satellites in orbit need corrections for time dilation to maintain accurate navigation on Earth. Two critical concepts arise from special relativity: time dilation and length contraction. Time dilation means that time slows down for objects moving at high speeds. This could theoretically allow for long-distance space travel, where astronauts could experience only a few months while years pass on Earth. Length contraction, on the other hand, states that objects in motion appear shorter in the direction they are moving. This effect is only noticeable at speeds close to the speed of light, making interstellar distances appear shorter for high-speed travelers. Together, these concepts reshape our understanding of time, space, and even the feasibility of human space exploration. One of the most famous outcomes of special relativity is the equation E equals mc squared, which reveals that energy is equal to mass times the speed of light squared. This equation implies that mass and energy are interchangeable, meaning that even a small amount of mass can release a tremendous amount of energy. This principle forms the foundation of nuclear energy and explains why stars emit so much light and heat through nuclear fusion. In nuclear reactions, tiny amounts of matter are transformed into vast quantities of energy. This equation also led to predictions about antimatter and other exotic forms of matter, enriching our understanding of particle physics and cosmology. Despite its success, relativity isn't without challenges. General relativity, which describes large-scale phenomena like stars and galaxies, doesn't align well with quantum mechanics, which governs atomic and subatomic particles. The pursuit of a unified theory that combines both realms, often called the theory of everything, is one of the biggest goals in theoretical physics, with approaches like quantum gravity and string theory attempting to bridge this gap. Furthermore, general relativity's predictions about black holes and singularities hint that our understanding of space-time might still be incomplete. Observations of phenomena like dark energy, which accelerates the universe's expansion, suggest there are aspects of physics yet to be discovered. Though it may seem abstract, relativity has practical applications in everyday life. For instance, the Global Positioning System, GPS, relies on relativity-based adjustments, as satellites orbiting Earth experience different gravitational and speed effects on time. Without these adjustments, GPS accuracy would quickly degrade. Relativity also plays a crucial role in particle accelerators, which must account for relativistic effects as particles approach light speed. The Large Hadron Collider, for example, uses these principles to ensure the accuracy of high-energy particle physics experiments. In summary, the theory of relativity transformed how we perceive the universe by demonstrating that space and time are interconnected and can be influenced by gravity and motion. General relativity redefined gravity through space-time curvature, while special relativity reshaped our understanding of time, speed, and energy. Together, these theories form the backbone of modern physics and continue to inspire new technological and scientific advancements. But relativity is only the beginning. As we venture further into the mysteries of black holes, time travel, and the expanding universe, we may yet uncover even more mind-bending truths about reality. Now, let's explore the next mind-bending concept: quantum mechanics. This theory explains the behavior of particles at microscopic scales, where classical physics no longer applies. Quantum mechanics introduces us to a world governed by probabilities, uncertainties, and phenomena that challenge our understanding of reality. One of the cornerstones of quantum mechanics is wave-particle duality, which suggests that particles like electrons and photons can behave both as particles and as waves. In the classic double-slit experiment, particles fired at a barrier with two slits create an interference pattern, behaving like waves. However, if we observe which slit each particle passes through, they act like particles again, as though the act of measurement changes their behavior. This mysterious link between observation and reality questions the very nature of existence. Next, we have the uncertainty principle, proposed by Werner Heisenberg in 1927. It states that we can't know both the exact position and momentum of a particle at the same time. The more precisely we know one, the less precisely we can know the other. This isn't due to measurement limitations, but is a fundamental property of quantum particles, adding an element of randomness and unpredictability to the quantum world. Imagine you have a ball moving along a path. In classical physics, you can measure both its speed and position accurately. However, in quantum mechanics, if you try to measure an electron's exact position, you inherently alter its momentum, making precise measurement impossible. Quantum superposition takes uncertainty a step further. It states that particles can exist in multiple states simultaneously until observed. Erwin Schrödinger famously illustrated this with a thought experiment: Schrödinger's cat. Imagine a cat in a sealed box with a vial of poison. If a radioactive atom decays, the vial breaks, killing the cat. Until we open the box, the cat is in a superposition of being both alive and dead. This paradox highlights how observation affects outcomes in the quantum world. Superposition has practical applications, especially in quantum computing. Quantum computers utilize qubits, which can exist in multiple states at once, allowing them to perform vast amounts of calculations simultaneously. This gives quantum computers the potential to solve complex problems far beyond the reach of classical computers. Quantum entanglement is one of quantum mechanics' strangest phenomena. When particles become entangled, the state of one instantaneously affects the state of the other, no matter the distance. If we measure one particle, we instantly know the state of the other, even if they're light years apart. This phenomenon, called spooky action at a distance by Einstein, challenges the idea that objects are only influenced by their immediate surroundings. Entanglement has significant implications for quantum communication and cryptography. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems exist in superposition until observed, causing them to collapse into one definite state. This raises profound questions. Does reality depend on consciousness? If observing a particle can change its state, what role does our mind play in shaping the physical world? This interpretation bridges physics with philosophical debates about the nature of reality. In contrast to the Copenhagen interpretation, the many worlds interpretation proposes that all possible outcomes of a quantum event actually occur, each in a separate universe. For example, in Schrödinger's cat experiment, one universe would have a live cat and another would have a dead one. The many worlds interpretation implies a multiverse of branching realities, each representing different outcomes, avoiding the need for wave function collapse. While it sounds like science fiction, this interpretation has gained popularity among physicists. Quantum mechanics has led to groundbreaking advancements in technology, especially in computing, cryptography, and telecommunications. Quantum computers, for example, use qubits that can represent both 0 and 1 simultaneously, enabling them to solve complex problems much faster than classical computers. Quantum cryptography uses entanglement to develop unbreakable encryption methods. Quantum teleportation, although not teleportation in the science fiction sense, uses entanglement to instantly transfer information, potentially revolutionizing secure communications. Quantum mechanics presents philosophical and scientific challenges that stretch beyond physics. Unlike the deterministic world of classical physics, the quantum world introduces probabilities, where outcomes depend on observation, challenging ideas of objective reality. Quantum mechanics has inspired numerous interpretations and debates. Is reality independent of observation, or does our consciousness shape it? These questions bridge the realms of science and philosophy, making quantum mechanics one of the most existentially provocative theories. To summarize, quantum mechanics defies conventional understanding with concepts like wave-particle duality, uncertainty, superposition, and entanglement. This theory challenges classical physics, introducing a probabilistic and interconnected universe that pushes the boundaries of what we know. Quantum mechanics has paved the way for technological breakthroughs in computing and cryptography, yet leaves us questioning the nature of reality itself. As we journey deeper into these mysteries, quantum mechanics will continue to shape our understanding of the universe and invite us to rethink reality. Let's move on to string theory, an ambitious and mathematically complex theory that aims to unify all of the fundamental forces in nature and provide a theory of everything. String theory suggests that the fundamental building blocks of the universe aren't particles like electrons or quarks, but incredibly tiny, vibrating strings. These strings and their vibrations supposedly give rise to all particles and forces, making string theory one of the most promising yet confusing approaches in modern physics. At its core, string theory proposes that the building blocks of our universe are one-dimensional strings. Each string vibrates at a specific frequency, producing different particles and forces, similar to musical notes on a string instrument. For example, an electron and a photon would both be different vibrational patterns of a fundamental string, much like different notes produced by the same string on a musical instrument. One of the revolutionary aspects of string theory is its potential to unify quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. While quantum mechanics explains the behavior of particles and relativity explains gravity, these two frameworks are currently incompatible. String theory could provide a way to reconcile them by offering a single, coherent framework that accounts for all known forces and particles. Multiple versions of string theory emerged in the 1980s, leading to confusion. However, physicist Edward Witten introduced M-theory, uniting these versions into one overarching framework. M-theory suggests that strings may not be the only fundamental structures. Higher dimensional objects called branes, short for membranes, might also exist. These branes could be as small as a single point or as vast as a universe, adding a whole new layer of complexity to the theory. According to M-theory, our own universe might be a three-dimensional brane floating within a higher dimensional space, possibly interacting with other branes and universes. One of the most challenging and mind-bending aspects of string theory is its requirement for additional spatial dimensions. In everyday life, we experience 3 dimensions of space and 1 dimension of time. However, for string theory's equations to work, 10 or even 11 dimensions are required. The additional dimensions in string theory are hypothesized to be compactified or curled up so small that we can't perceive them. Imagine a 2-dimensional sheet of paper curled into a tight spiral. If you zoomed out far enough, it would appear as a 1-dimensional line. In a similar way, the extra dimensions in string theory could be curled up to scales smaller than an atom, making them invisible to us. The idea of extra dimensions, while mathematically sound, is almost impossible to visualize, adding to the confusion and intrigue surrounding string theory. These dimensions could hold the key to understanding forces that seem weak or mysterious in our familiar dimensions, such as gravity. Because string theory allows for many possible solutions, there may be an enormous number of vacua or possible configurations of the universe. Each configuration would correspond to a different set of physical laws and constants, leading to the possibility of a multiverse, an immense collection of universes, each with its own distinct properties. In other words, our universe could be one among countless others, each governed by different rules. This idea is both intriguing and problematic. If the multiverse is real, it would be impossible to test or observe directly, meaning we may never confirm or falsify its existence. Critics argue that this makes string theory difficult to treat as a true scientific theory, as it may lead to predictions that cannot be tested or observed. Despite its promise, string theory faces challenges. It lacks testable predictions, is mathematically complex, and some question if it qualifies as a scientific theory due to its non-falsifiable nature. Even without concrete proof, string theory has profoundly impacted physics and mathematics. Concepts from string theory have influenced quantum field theory and pure mathematics, leading to insights that extend beyond its original scope. Physicists continue refining string theory, hoping that future experiments or new technology will reveal supporting evidence. String theory offers a path to unify all fundamental forces, potentially revealing a theory of everything. Whether it leads to a revolutionary understanding or paves the way for future theories, string theory marks a bold step in our quest to unravel the cosmos mysteries. Approximately 13.8 million years ago, an enigmatic occurrence propelled the universe into motion, marking the advent of the Big Bang, an extraordinary event that gave rise to every atom, star, and galaxy. However, what unfolds here is uniquely ours, a saga spanning millennia where we've endeavored to construct a vision of the universe. This endeavor, guided by the principles of science, has allowed us to fathom our place within the vast cosmos. Over thousands of years, we've documented our celestial observations in volumes that could easily populate a library. The edifice of knowledge we've erected regarding our universe encompasses its origins and contemplates its eventual conclusion. So where does our narrative commence? Let's embark on this journey from the very outset. Let's delve into the genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution and unfolding narrative that illuminates how the universe transformed in the blink of an eye. The very nature of what sparked this cosmic genesis remains an unsolved puzzle to this day. As we peer into the vastness of the universe and contemplate distant galaxies, a mesmerizing panorama unfolds. everything appears to be receding from us, propelled outward at astonishing speeds. We string that all the way back, we glimpse a singular moment, perhaps 13 or 14 billion years in the past, where all matter was inexplicably condensed into an inconceivably dense point. The Big Bang stands as our prevailing theory, a testament to our attempts to decipher the universe's inception. For an extended period, contemplation of the universe's origin was not a common pursuit. Some didn't dwell on it, while others assumed the cosmos had perpetually existed, an everlasting entity shrouded in mystery. Initially, even scientists hesitated to embrace the concept of the Big Bang. Originally intended as a somewhat derisive term, the name itself poses a paradox. It wasn't particularly big, considering our belief that the universe originated from a singularity, and there was no literal bang since there was no air to transmit vibrations. Today, the Big Bang theory is a well-established pillar of science, widely accepted and understood. However, acceptance and comprehension are distinct realms. While the Big Bang theory has solidified its place in our understanding of the universe, it hasn't yet unraveled all the mysteries science seeks to answer about the birth of our cosmos. Conventional Big Bang theory remains silent on what triggered the bang, why it occurred, or what transpired before it. At this very moment, we find ourselves in the aftermath of the Big Bang. Everything what we see and hear and taste and smell and touch is aftermath. This is the Earth, a marvel of silicon and oxygen encasing a metallic core. Its surface is dominated by vast oceans, fostering a diverse array of life. In a rhythmic dance, the Earth completes a full rotation every 24 hours while encircling the radiant star known as the Sun, completing an orbit every 365 days. The Sun, a radiant giant predominantly composed of hydrogen and helium. With a scorching surface temperature nearing 10,000 degrees Fahrenheit, this cosmic powerhouse converts a staggering 700 million tons of hydrogen into 695 million tons of helium every second. This celestial luminary is at the heart of our solar system, which took shape approximately 4.5 billion years ago. This system has 8 planets, from the sweltering Mercury to the frigid Neptune. Our solar system is no static entity, hurtling through space at a staggering 134 miles per second. It is part of a vast congregation of stars and stellar systems. This congregation, known as the Milky Way galaxy, around 200 billion stars. Among these, an estimated 6 billion may harbor planetary systems akin to ours. Our solar system orbiting the center of the Milky Way on one of its outer arms is just one member of a grand ensemble. The Milky Way is merely one among the vast expanse of more than 125 billion galaxies, constituting the observable universe. Indeed, the universe is colossal, and its enormity continues to expand. If we rewind time, we can witness the universe shrinking from a cosmic scale to a galactic one, then to the dimensions of our solar system, and further still until everything is confined within the confines of a studio, a coffee cup, and ultimately an atom. The vastness of the universe unfolds before us, a cosmic narrative expanding across unimaginable scales. Physicists have pieced together an approximate timeline of significant events in the cosmos' existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion 10 trillion degrees Fahrenheit or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch, the subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to be out without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost 1 billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.6 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the Sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little, primitive bacteria appeared on that third, watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end or not? It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Everything we know represents just 5% of the universe. What is the rest? Normal matter protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in spacetime. This is known as the 4-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the four-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the four fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our four-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the Anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the spacetime continuum, which is the four-dimensional fabric of the universe, consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature. In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no-communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the Anthropic principle, which states that the universe is the way it is, because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us, because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes, that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist either. Next, let's examine black hole paradoxes, some of the most puzzling and intriguing enigmas in astrophysics. Black holes, regions in space where gravity is so intense that not even light can escape, have long fascinated scientists and the public alike. But these cosmic phenomena challenge our understanding of space-time and the fundamental laws of physics, particularly when it comes to information, causality, and entropy. Black hole paradoxes. What is a black hole? A black hole is a region in space with such an extreme gravitational pull that nothing, not even light, can escape from it once it crosses the event horizon, the boundary beyond which escape becomes impossible. Black holes are thought to form when massive stars collapse under their own gravity, compressing matter to an infinitely dense point called a singularity. At this singularity, gravity becomes infinitely strong, and the known laws of physics, particularly general relativity, break down. The event horizon, while invisible, represents the point of no return around a black hole. Anything that crosses this boundary is doomed to be pulled into the singularity, losing all connection with the outside universe. Despite being invisible, black holes reveal their presence by exerting a gravitational influence on surrounding matter, bending light and emitting X-rays when they consume nearby matter. The information paradox. One of the most famous puzzles associated with black holes is the information paradox, a problem that questions the very nature of reality. It arises from a conflict between quantum mechanics and general relativity. The basics of the paradox: according to quantum mechanics, information is never truly lost. When matter falls into a black hole, it carries information about its properties such as mass, charge, and spin. However, if this information is permanently trapped or destroyed within the black hole's singularity, it violates quantum mechanics' principle of information conservation. Hawking radiation. In the 1970s, physicist Stephen Hawking proposed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon, a phenomenon now known as Hawking radiation. Over time, as a black hole emits Hawking radiation, it gradually loses mass and energy, eventually evaporating and disappearing altogether. However, if a black hole evaporates completely, what happens to the information that fell into it? Hawking initially argued that the information would be lost, challenging the fundamental principles of quantum mechanics. Potential solutions: information conservation. Some theorists argue that information is somehow encoded in the Hawking radiation itself, preserving it even as the black hole evaporates. This solution suggests that the radiation carries subtle clues about the matter that fell in, although no one has definitively demonstrated how this would work. Holographic principle. The holographic principle proposes that all the information within a black hole is stored on its event horizon, like a 2D surface encoding information about a 3D space. This principle, inspired by string theory, suggests that the universe itself might be a kind of hologram, with all the information on its boundary. This concept could solve the information paradox by ensuring that information remains accessible, even if the black hole itself vanishes. Wormholes and firewalls. Some theories propose that information might escape through hypothetical wormholes or other quantum phenomena connecting the black hole to other regions of space. Another possibility is the firewall hypothesis, which suggests that an intense wall of energy forms at the event horizon, burning up any information before it crosses into the black hole. This idea is controversial, as it challenges long-standing assumptions about black holes and quantum mechanics. The information paradox remains unsolved, but it's an active area of research. It forces physicists to rethink fundamental aspects of quantum mechanics, relativity, and the nature of spacetime, spaghettification, and what happens inside a black hole. Another fascinating phenomenon associated with black holes is spaghettification, a term that describes the extreme stretching objects undergo as they approach the event horizon. This effect occurs because gravity increases dramatically as one gets closer to the black hole. For example, if an astronaut fell feet first toward a black hole, the gravitational pull on their feet would be much stronger than on their head, stretching them like spaghetti. The closer one gets to the singularity, the more extreme this stretching becomes, eventually tearing matter into its most fundamental particles. However, since our understanding of physics breaks down at the singularity, what happens to matter beyond a certain point remains unknown. Inside a black hole, space-time might curve infinitely, creating an environment where traditional concepts like time, space, and causality cease to function. Time dilation and the nature of space-time. One of the unique features of black holes is their effect on time. Due to their extreme gravitational pull, time behaves differently near a black hole. According to general relativity, time slows down in strong gravitational fields. Near the event horizon of a black hole, time dilation becomes so intense that, to an outside observer, time for someone falling in appears to slow to a crawl. In theory, if someone observed a clock at the event horizon, it would seem frozen. This extreme time dilation has implications for the nature of black holes and the information paradox. As a person approaches the event horizon, they would experience time normally, but to an observer outside, they would appear to freeze in place. This dual perspective raises questions about whether information or matter ever truly crosses the event horizon from an outside perspective, or simply becomes frozen there in some form. Black hole thermodynamics and entropy. Another paradox of black holes involves entropy and thermodynamics. In classical physics, entropy, a measure of disorder, always increases, reflecting the irreversible nature of time and events. When matter falls into a black hole, its entropy seemingly vanishes, which would violate the second law of thermodynamics. To address this, physicists have suggested that black holes possess their own entropy, which is proportional to the area of their event horizon rather than their volume. This relationship, known as the Bekenstein-Hawking entropy formula, implies that as a black hole absorbs matter, its event horizon expands, increasing its entropy. This insight not only preserved the second law of thermodynamics, but also led to the concept that black holes have temperature and can emit radiation, Hawking radiation. The thermodynamic properties of black holes suggest that they could be more like physical systems with measurable entropy and temperature than previously thought. Understanding black hole thermodynamics may also lead to insights into quantum gravity and the nature of space-time. Potential solutions to black hole paradoxes. Physicists have proposed various solutions and theories to address the paradoxes associated with black holes' holographic principle. As mentioned earlier, the holographic principle posits that all information about a black hole's contents is encoded on its event horizon. This theory, rooted in string theory, suggests that the universe itself might be a hologram, with all information about three-dimensional objects stored on a two-dimensional boundary. The firewall hypothesis, though controversial, proposes that a blazing firewall of high-energy particles exists at the event horizon, destroying anything that attempts to cross it. While this idea solves certain paradoxes, it conflicts with general relativity's predictions that someone crossing the event horizon would experience no immediate change. quantum gravity theories, one of the most promising approaches to resolving black hole paradoxes is the development of a theory of quantum gravity. Quantum gravity aims to unify general relativity and quantum mechanics into a single coherent framework. This theory could provide a more complete understanding of black holes and explain what happens at the singularity and to information within black holes. Wormholes and quantum entanglement. Some theories suggest that black holes could be connected to other regions of space through wormholes or Einstein-Rosen bridges. These connections might allow information to escape, preserving it without violating quantum mechanics. In this view, quantum entanglement could play a role in linking black holes with other parts of the universe. Implications of black hole paradoxes on physics. Black hole paradoxes have profound implications for physics, challenging our understanding of space, time, and the fundamental laws of the universe. The unresolved nature of the information paradox suggests that there may be unknown principles or deeper levels of reality we haven't yet grasped. In unified theories, black holes force us to reconcile general relativity, which describes gravity on a cosmic scale, with quantum mechanics, which governs the subatomic world. Finding a unified theory or a theory of everything may require us to rethink our understanding of space-time, gravity, and fundamental particles. Insights into the universe's beginning and end. Some theories suggest that the conditions within black holes could mirror those of the universe at the time of the Big Bang. By studying black holes, physicists might uncover clues about the origin of the universe, or even its eventual fate. Nature of reality and information. The information paradox suggests that information is preserved in some way, even in extreme environments. This could have profound implications for our understanding of reality, suggesting that information is a fundamental property of the universe and might transcend traditional boundaries of space and time. Potential for new physics. Black holes represent the frontier of physics. The unresolved paradoxes they pose may lead to revolutionary discoveries, revealing new laws of nature or even entirely new realms of physics. Concepts like quantum gravity, holography, and wormholes are just beginning to scratch the surface of these mysteries. Black hole paradoxes, such as the information paradox and the nature of space-time near the event horizon, challenge our deepest understanding of physics. These paradoxes raise profound questions about the nature of reality, time, and information, suggesting that our current theories may be incomplete. Through the study of black holes, scientists hope to uncover insights into quantum mechanics, relativity, and perhaps even a unified theory of physics. The unresolved mysteries of black holes continue to drive research and inspire new theories, pushing the boundaries of science and philosophy. As we seek answers to these paradoxes, black holes may ultimately reveal some of the universe's most hidden secrets. With black hole paradoxes covered, we now move to another fundamental and mysterious aspect of quantum physics: quantum entanglement. Known as spooky action at a distance, entanglement challenges our understanding of locality and may hold the key to faster-than-light communication and the nature of reality itself. In the constellation Cygnus, roughly 7,800 light-years from Earth, lies one of the universe's intriguing cosmic landmarks, V404 Cygni, known for its intense eruptions of energy. When the black hole draws material from its companion, this typically results in immense bursts of energy and light, offering a vivid display of gravitational forces in action. Recently, V404 Cygni revealed something unexpected. It isn't a simple binary system as previously thought. New observations reveal it as a rare triple system, with a third stellar companion orbiting the black hole and its close partner at an astonishing distance. This newly identified third star circles around the inner binary, adding depth to the structure and complexity of V404 Cygni. This stellar system has long been known for its inner binary structure, where a black hole and a neighboring star orbit each other. The black hole, an extremely dense remnant of a massive star, exerts a powerful gravitational force on its companion, a star with characteristics similar to our Sun. This dynamic pairing leads to what is known as an accretion process. As the black hole draws material from the outer layers of its companion, the matter heats up, spiraling toward the black hole in a swirling disk known as an accretion disk. This process not only results in the release of high-energy particles but also produces intense flashes of light and X-rays detectable from Earth. The orbits in this binary relationship are remarkably close, with the black hole and its star companion completing an orbit every 6.5 days. This tight orbit amplifies the accretion process, causing frequent eruptions of energy that, while relatively brief, are powerful enough to be observed by telescopes even from such a great distance. These observations have provided astronomers with insights into the behavior of black holes within binary systems and have contributed significantly to our understanding of how black holes interact with other celestial bodies. Scientists believe that studying systems like V404 Cygni helps explain similar cosmic events and processes across the universe. Recently, scientists using advanced observation techniques uncovered a surprising third component in the V404 Cygni system. This third star, unlike the two members of the inner binary, orbits at a considerable distance, about 3,500 times the distance from the Earth to the Sun. It completes an orbit only once every 70,000 years, making it the outermost member of this rare triple configuration. This discovery redefines V404 Cygni as it shifts from a typical black hole binary to a hierarchical triple system, with two components tightly bound and a distant third companion on a much longer orbit. To detect this outer star, researchers utilized precise imaging techniques, relying on data from telescopes capable of capturing minor distortions in the system's light patterns. These subtle shifts provided clues that something beyond the inner binary was influencing the gravitational dynamics at play. As the first black hole system of its kind to be observed, V404 Cygni now offers a unique example of how multiple stars might interact with a black hole over enormous distances. The presence of this third star challenges traditional theories about the formation and stability of black hole systems, suggesting that such systems may have formed differently from other black hole binaries. Traditionally, black holes were thought to form from supernova explosions, cataclysmic events that result in the remnants of massive stars collapsing. The intense energy released during these explosions would generally disrupt the surrounding stellar structures, making it difficult for any nearby stars to maintain stable orbits. However, in the case of V404 Cygni, the presence of this third star orbiting at such an expansive distance suggests an alternative scenario. One hypothesis gaining traction is that the black hole in V404 Cygni may have formed through a direct collapse rather than a supernova. This means that instead of exploding, the massive star that eventually became the black hole might have gradually imploded, avoiding the shockwaves that usually accompany a supernova. This gentler formation process would allow a distant companion, like the third star in V404 Cygni, to maintain its orbit without being ejected or disrupted. If correct, this theory would indicate that black hole systems can evolve in ways previously unconsidered, potentially leading to the discovery of more quietly formed black holes with companion stars that survived the process. Beyond the structural insight, this discovery has implications for black hole research as a whole. Understanding the different ways black holes can form helps astronomers refine models of stellar evolution and gravitational dynamics. The unique configuration with its stable third star orbiting a powerful black hole might serve as a blueprint for identifying similar systems. It also raises questions about how many black holes in our galaxy may have formed through this gentler process and what that means for the diversity of black hole systems within the Milky Way and beyond. The discovery of this unique system has opened up new horizons in black hole research, sparking interest in finding more examples of such unique configurations. Scientists are eager to explore whether other black holes might also form in similarly quiet processes, keeping their companion stars intact rather than expelling them. Future observations and studies on this triple system could provide more answers, allowing researchers to probe deeper into questions about black hole origins and evolution. By mapping out the orbits and movements of the three components in V404 Cygni, they hope to gain clearer insights into how gravitational forces operate in complex black hole systems. These findings may lead to refined models of black hole formation and perhaps reveal additional systems with similar structures across our galaxy. As scientists continue their search, V404 Cygni stands as a testament to the surprises that space still holds. This discovery is just one chapter in the ongoing story of black holes, and it leaves us with a sense of anticipation for what might come next in our exploration of the universe's most mysterious entities.